screen here. Yeah, so just a couple of logistics things. We will start the tutorial from tomorrow. I think should have got a calendar invite, and then I should have sent you, right? So if you people have time, so please join the tutorial. Otherwise, you can access it later. And we will start the quizzes from next week. Okay, so which means like the second Saturday from today. So today is 31st August, right? Wednesday, next Saturday.
14th, I believe.
14th, na? Yeah, yeah. We will have our first quiz on 14th. Okay.
Sir, can we
Hmm.
have the tutorial either on Saturday evening or any of the weekday evenings? Sunday is one day we can leave.
See that, right? That please talk to coordinate with the TA, because I believe that he had a poll or something. Did he?
No, sir.
No.
No, really?
No, I
No,
don't think so.
I think we didn't got it.
Surprising. Let me just call him right away and just settle that. Just give me a minute.
So there was a poll actually.
There was a poll
Is
in the
it?
channel. Yeah, there's a poll in the channel.
Then okay, right? I mean, I think the
How when it came actually, in the chat window, or you didn't
No, in
saw
the
it on.
channels, in the general of this channel, there's a poll.
Oh, okay.
yeah. So then it's fine, right? It was decided based on the outcome of that poll, I suppose, right?
There were only
And in
34
the
answers.
evening, there are another tutorials also like for random process and linear. Today.
What can we do? Okay, so let me ask him to have another poll perhaps and then decide. Just a second, let me call him.
ನೀವು ಕರೆ ಮಾಡುತ್ತಿರುವ ವ್ಯಕ್ತಿಯು ಉತ್ತರಿಸುತ್ತಿಲ್ಲ.
He's not picking it up. He'll call back. Once he calls back, I'll tell him. See, I mean, it's very difficult to find a time that is convenient for like all 100 people in the class. Okay, so I mean, we have to do something. So yeah, so whatever works for most of the people, we'll have to stick to that. So I'll ask him to have the poll again, and then we can decide. Okay, where is this thing? Yeah, it is here. You see my screen?
Not yet.
This says it is being shared. No, it says it is being shared here. How come? Okay, let me rejoin. Yeah, tell me. Yeah, please go on. Somebody put it.
Yes, sir.
Yeah, tell me.
Yeah, we are able to see it.
Okay, shall we start?
Yes, sir.
Yes.
Oh, good. Yeah. So a little bit of recap before we continue with today's content. Um, yeah. So we were looking at the relevant probability theory stuff, right? So we have the probability triplet, which is the sample space, the event space, and probability measure, and we define this function called random variable that would give you this push forward measure, right? Yeah. So then we said that once you have this function called random variable, that will move the sample space to some d-dimensional real numbers, and you have subsets of real numbers, and then you have the corresponding measure, probability measure that gets translated into the real space, which we call the distribution function, right? And we looked at some of the properties of what distribution functions are and looked at multiple random variables, conditional random variables, independence, right? And joint random variables and so on. Okay. Um, okay. Before I go to the supervised learning part, machine learning part, any questions on the probability theory part?
Hello, sir.
A second, I have to open that. Yeah. Okay. Yeah. Go on, Sachin.
I just have one question from last lecture. So you
Hmm.
mentioned that Borel sigma algebra. So we just last week studied that in recent process class, and
Oh,
that was
nice.
defined on 0 to 1 interval, right? All open-ended intervals. So I was just asking for this the problem you mentioned. This Borel sigma algebra is defined on minus infinity to infinity, or like it is always on 0 to 1.
Uh, See, Borel sigma algebra for the real numbers, right? They are defined on real sets, right? I
Right.
think you have confused, right? Why is it between 0 and 1?
No, he just gave an example, so that's
No,
why I
you
was
can take
asking.
any set and generate
Any
Borel
set
sigma
and all
algebra.
open.
Yeah, you can take any set and generate a sigma algebra on top of it, right?
Right, sir.
But specifically, Borel sigma algebras are defined on real numbers, right?
Real numbers. Okay.
Yeah. Yeah, smallest sigma algebra on R that contains all the intervals that are possible. That is the full sigma algebra. Yeah. See, that is why I did not even take I mean, to define Borel sigma algebra, right? I said like R, RD, and subsets of RD, and then you have the distribution function on top of it, right? Okay. Let's move on. Anything else? By the way, Sachin, who is teaching random process? Is Aditya teaching it?
Yes, sir. Aditya Gopalan, sir.
Okay. Yeah, we are very good friends. Yeah. Okay. With that, we will look at what supervised machine learning is. I said that the data, right, is defined as some n samples, okay, that are drawn. Yeah, that is what I know. The notation is that you have data sampled from a particular distribution or data drawn from a distribution. Yeah, that actually boils down to saying that every data point that we have is an element from the range space of a random variable that we have, that is x. Okay, I mean that we denote by x. So this implies that there exists an underlying probability measure and thus the distribution function induced by x. Okay, so this is clear, right? So whenever we say that we have n data points, we actually mean that we are sampling, I mean we have n vectors from the range space of the random variable. Once we talk of the range space of the random variable, uh, we we understand that there has been, I mean, there is an underlying measure space, there's underlying sample space that is there, and a probability measure, and therefore a distribution function induced by X. Okay. Now, for the so-called supervised learning, what happens is that you have data sampled from the joint distribution of a pair of random variables X and Y. Okay, where X denotes a random variable whose range space is some RD. I mean, I gave the example of MNIST, right, where it is R784 dimensions, because the images are in 28 cross 28 pixels, and Y, which is the is another random variable that we are talking of, denotes the labels, so-called labels, and there exists two sample spaces, right? Or yeah, so two sample spaces whose cross product is what we are talking about when we talk of joint distributions. And when we say data, this is what we mean, right? We have basically, right, in other words, what we are saying is obtaining data is equivalent to conducting the underlying random experiment that generated your sample space multiple times. That's what it means, right? We have conducted the we are actually running the random experiment multiple times. We are making multiple trials, right? And each of the trial gives rise to some sort of an outcome, okay? And that outcome gets mapped to some d-dimensional real space via random variable. And because we are looking at a random experiment, there is a probability measure that we have assigned, and because since we have a random process, random variable, I'm sorry, wait, excuse me, because since we have a random variable, um, you have, I mean, the outcomes of these experiments have been converted into something measurable, that is a d-dimensional real number. That is what is happening. Uh, is this worldview clear? See, from now on, right, I will not tell you that these are actually vectors in the range space of a random variable, which is a function, and you have the underlying measure, and you have the distribution, etc. I will simply say that we are given a data from an underlying distribution. That's all. So you should understand what I mean when I say that. Is this clear? Any questions on this? Okay, so now let us start with the definitions. Does this libraries? Oh, I don't know what this is. Okay.
Sir, you need to select plus page in the third column.
This page. Okay.
Then you can mention the title.
We're also putting lecture numbers, right? L3. Say. Yeah. So we'll mostly set up the problem today, right? What is the generative modeling problem and so on. Okay. So that is what the major focus of today's lecture is. Okay. Now let us start with the data. So this is our input, right? Means this is, as they say, I always represent data with set. So it is either. So let us first maybe set up supervised machine learning. Actually, right, at a core level, there isn't a lot of difference between supervised and unsupervised machine learning. I will tell you why it is. will it be from a comprehensive standpoint? Will it be better to introduce can all of you mute, please? Let me do that. Okay, so let me introduce in general, then we will talk of the differences. Okay, data. So let's say that you have data. Data is of this form: x1, x2, xn. Make it a little abstract from now on, xn. And these has been drawn from some underlying distribution px, and this is unknown. So this is the setting, right? So now this actually means that this keeps happening. I keep my palm over the screen, right? It just gets distorted. I don't know how to control it. Let me know if somebody knows how to do that. Anyway, so this is thing. We have data that is drawn from an unknown distribution. So actually means that this is the central problem of machine learning, that data, right, are samples from an unknown distribution. Okay. Okay, so this actually means that the distribution is unknown, but we have samples from it. So this is the central problem of machine learning in our statistics, that you have samples from a distribution, but you don't know what the underlying distribution is. Okay, so now the question that we ask, the central question that is asked in ML is the following: that given samples from a distribution, okay, estimate the distribution. Estimate the underlying distribution. So this happens to be a central question in ML, that if you have if you are given samples from a distribution, can you estimate the underlying distribution? Okay. Now, why is this important? You understand the question, right? They are two different things. Having samples from a distribution is different from knowing the distribution itself. Can you see the difference? Can all of you see this difference? This is very, very important. Okay.
Yes, sir.
So now, so the question is, if you are given some samples from the distributions, you have to estimate the underlying distribution. So why is this of importance is the question. Okay. The thing is, this is important because, now let me write that down. Knowing the distribution enables prediction / sampling. Okay, this is the claim. So if you know the distribution, okay, you can do prediction and you can do sampling. So now what do you mean by prediction and sampling is, that see in supervised machine learning, the problem is that of prediction, and in unsupervised machine learning, mostly the problem is of sampling. All right, in generative models, the problem is of sampling. Now, to do both, so I request all of you to kindly mute yourself. Okay, so unmuting with some noise will just cause some disturbance. Thank you. Yeah, so knowing the disturbance, uh, you see, knowing the distribution enables prediction and sampling. Okay, now what do I mean by this is the question. So now let's say that you have um, so let's take some examples. First example may be that, so given the pairs of images and labels, okay, I'll put it in quotes because I've not defined this yet. Learn to predict learn to predict the labels of unseen images. Right? This is the classical classification problem, right? Given pairs of images and labels in terms of data, learn to predict the labels of unseen images. So now my claim is that you can model this in the language that we have just said. So now let's say that the data that has been given is the following, that you have pairs of x and y. So note that whenever I write this, I mean that there are two random variables that are there, and the data has been drawn from an unknown joint distribution between x and y, right? So this is given pairs of images of given the pairs of images and labels. Now, how do you define this learn to predict part of it? Okay, so now prediction is defined as the following. Prediction is defined to be evaluate the likelihood of label given an image. This is the definition of prediction problem. I will define what likelihood is. Okay, now we'll have to define likelihood, right? So likelihood, okay, likelihood of, this is a very important terminology, likelihood of a point x is defined to be the value of the density function, call this as x cap. Okay, density function evaluated at x cap. So this is the definition of the likelihood. So note that I'm not calling it a probability because I'm evaluating the density function. Remember last class I told you that evaluating the density function of a continuous random variable will not give you the probability, right? So that is why I'm defining likelihood of a point as the value of the density function evaluated at x, okay, at some point x. This means that uh, suppose you have a point, suppose there is some x cap that is in some RT, okay, and Px is a density function. Then the likelihood of x cap is simply the density function evaluated at x cap. Is this clear? Please note the notations here. Whenever I talk of distribution functions, right, I write this script P, double line P. Whenever I write the density functions, I write small p, okay? And in most of the rest of the part of this course, we will work with density functions, not the distribution functions, okay? Simply because they are easy to work with, okay? And remember the connection between the density function and distribution functions, right? Distribution functions are valid probability measures, okay? And the derivative of the distribution functions are what are called as the density functions. Density functions evaluated at a particular point will not give you probabilities, but density functions integrated over a range will give you probabilities, because that would be the distribution function evaluated at a particular point. All this is clear, right? Just repeating what we did in the last class. Okay, great. So now likelihood,
so just one point.
Yes, go on.
So you mean to say the likelihood function is the same as the probability density function?
Likelihood, yeah. I am defining the likelihood as the density function evaluated at likelihood at a point is equal to the density function evaluated at that point.
Okay.
That's the definition of likelihood. See, whenever we talk of likelihoods, right, the definition is that it is the density function evaluated at that particular point. Now, if the underlying random variable happens to be a discrete random variable, then evaluating density function becomes mass function, and evaluating the mass function at a point will actually give you probability, right? But in general, because we are looking at continuous random variables, density functions are not probabilities. That's why I don't want to call likelihood as probability of that particular point, because it does not mean anything. I would just want to define likelihood as evaluating, or likelihood of a point is simply the value of the density function evaluated at that point. And as we saw in the previous class, density function of a continuous random variable evaluated at a particular point can be more than one, okay? Can have values more than one, and it does not correspond to a probability. This much is clear, right? Okay. Now with the definition of likelihood function, we'll have to define what prediction is. Now I said prediction is simply evaluating the likelihood of the labels given an image, okay? Which implies that prediction is defined the following, that evaluate, okay, the conditional density at x cap. We'll have to say prediction at x cap, right? This prediction at x cap is evaluating the conditional density at x cap. So what does that mean? So suppose, or assume, let P of y given x denote the conditional density function of y given x. See, note that whenever there is a density function, there is an underlying distribution function, and I'm talking of conditional probabilities here, okay? Let P y given x denote the conditional density function of y given x. Then prediction at x cap is simply equal to evaluating this density function, okay, at I will explain my notation in a while, okay. At x is equal to x cap, okay. I will explain. Okay, let me explain the notation first. See, when I write the notational note, Okay. P of y given x denotes the following. So y given x. Okay. The subscript here denotes the random variables. Okay. Whenever I write the density function or any distribution function, anything, right? Subscript always denotes the random variables. This, which is whatever I write inside the parenthesis, right, denotes the value at which the function is being evaluated. Okay, is this clear? This is the notation. See, whenever I write conditional distributions, right, I always mean that the conditioned random variable, right, is fixed at some particular value x. See, this is the definition of conditional distribution, that when I write conditional distribution, it always means that the condition random variable is fixed to a particular value. So given that the condition random variable has taken a particular value, what does this density evaluates at? Is this clear? So now in this notation, the prediction, what does the prediction happen? What is the prediction problem? Prediction problem is, let's call that the prediction of x cap is simply the likelihood. Note that likelihood is a density function, likelihood, okay, of the conditional density y given x, okay, evaluated with the value of the conditioned random variable conditioned random variable. What is it? In this case, it is x, okay, fix that. This is the definition of prediction. See, whenever you talk of regression and classification problems, right, this is what you are doing. What you are doing is evaluating the density function, okay, conditional density function of labels conditioned on data, and you are evaluating that, okay, with the conditioned random variable, which is the data random variable fixed at a particular x cap. Because by definition, the conditional distribution always means that you have to fix the conditioned random variable at a particular value. So now, given that your conditioned random variable is fixed at a particular value, what does the density function evaluates to? That is called a prediction at x cap. Do you understand? Now, tell me this. Um, when we okay, so maybe before we go there, I will perhaps I'll tell you that. Okay. See, now suppose, let me take an example. Suppose y, okay, is a discrete random variable that takes value 0, 1, 2 up to k. Okay. Okay. If this happens, then prediction at x cap is what? What is this object? Can somebody tell me? and we will also fix x, and x, let's say x is some random variable that is in some 1000 dimensions. We are saying that there is an image, okay, it's a 100 by 100 image, 10,000 dimensions, 100 by 100 image, and we have k labels. So if I have to set up the prediction problem here, what does predicting give me? Can somebody tell me?
Argmax of P of y given
No,
x.
I have not defined it that way, right? Look at the definition.
One of the k labels.
No, it won't.
Probability density of y given x.
That is what I've, yeah. What do you mean by that? How many values does this give you? If you predict it on x cap, how many values will it give you?
Sir,
K.
it will give us
K
k
plus one.
values.
K plus
K
1.
plus 1.
K
Yeah,
plus 1.
it'll give you k plus 1 values, right? So now prediction here means that it give you an entire density function, in this case a mass function, because y happens to be a discrete random variable. So you have 0, 1, 2, up to k here, and this will have some values like this. Do you understand? So now this, what is this? This is the density function of y given x, right? Evaluated at x equal to x cap. Do you understand this? So now prediction will give you a distribution, sorry, it gives you a density function, right, or a mass function in this case, because it happens to be a discrete random variable, okay, which is evaluated at x cap. Is this clear? Any questions on this? Now, what do you do with this is a different question. See, now you can relate to what we were talking in the first class, right? Given some x, you want to know what the corresponding y is. In the deterministic case, right, or in the non-probabilistic treatment of stuff, what was happening is that for a particular x, you give a particular y. Okay. Now here, for a particular x, okay, you're giving me multiple y's with certain likelihoods associated with each of them. Is this clear? Now, what do you do with this? Is something that is specific to the user. Either I mean, most of the times, what do? We take one y, okay, corresponding to the maximum value of this density function, isn't it? If you, I mean, if you look at machine learning, what people do is we want one label, okay? So we don't want the density over labels. We want one label. Therefore, we take the argmax of this density and assign that as label for x cap. However, the problem is set this way that given a particular, like, what you are actually doing is you are evaluating the density function p of the conditional density function at that x cap. Is this clear? Any questions so far?
Sir, one question.
Hmm.
So this x cap means a particular point in the this x random variable.
You should be careful in choosing your words. Yeah. See, what do you mean by that? It's actually one of the points in the range space of the random variable, no?
Yeah, range space.
Yeah. But yeah, that is what it is. See, typically, right, x cap, typically x cap does not belong to the data set that you have, because that's the test data, right? That's what is called as test data. Right, even you're interested when you're talking about prediction, you can predict on x cap that belongs to D as well. But typically x cap does not belong to D, because you want to predict on unseen data, right?
Yes.
Okay. Yeah. So Vivek.
Sir.
Sir, is there any way we can visualize Py given x? I mean, P, what is that? Conditional random variable. Y.
What do you mean by visualize?
Visualize means
See, again, you have to go back to the previous lecture. I've told you that, but let me repeat. See, what is happening is that think of it like, there are two random experiments that are being done. One where the images are being taken, okay? The
Okay.
other where every
Okay.
image
It's
is,
a joint.
yeah, of course. I'm not talking
Okay.
about joint distribution. There is a joint distribution. Once you have a
Okay.
joint distribution, you have a conditional distribution as well. So we are saying
Correct.
that given that a particular outcome has occurred in one of the sample spaces, in the one of the trials, what is the likelihood, or like what is the probability that the other event happens, right? I mean, the other trial takes these particular values. That is what the conditional distribution talks about. Yeah.
Okay. Yes.
Hmm?
Yeah. Yeah.
Okay.
That's
Yeah. Raghavendra?
Yes, I mean, is there any particular reason why we take likelihood function to be a density function rather than the distribution function?
Yeah, I told you, right? It is easier to work with density functions. That's all. Most of the time, it is easier to work with density functions, especially when you have continuous random variables. It is easier to work with them. That's the only reason. Everything that you do with density function can be done with distribution functions. Okay. Not
Okay.
vice versa. Not vice versa. Everything that you can do with distribution functions can't be done with density functions, because there can exist random variables for which the density functions do not even exist.
Hmm.
But most of machine learning, we assume that density functions are well defined and they exist, and then we work with density functions. Typically in literature, not typically, right? In almost in everywhere in literature, likelihood is defined as the evaluating the density function at a point. Yeah, because of ease of computation and analysis. That's all. Yeah. You will see
Okay.
that more, when we talk of the divergence metrics, etc. in a while, you will see why density function is easier to work with. So also, right, there are lots of mathematical tools to deal with density functions. When we talk of random variables, we always talk of associate density functions, right? So uniform random variable, we give density functions. Distribution functions, we don't remember. Do you remember the distribution function of uniform random variable? No, no. And do you remember the distribution function of a Gaussian random variable? We don't, but we remember the density functions. That's the only reason. But you remember that whenever we talk of likelihoods are always density functions evaluated at a point. Okay. Okay.
Yeah.
Manikantha?
So the dimension here for the X cap will be 10,000, right?
Of course. Of course.
Okay.
X cap is not in D, right? But X cap is sampled from the same underlying distribution.
Yeah. Okay.
Srinath?
Sir, so I have a doubt. So this is the conditional distribution of P of X given Y.
Y given X?
How is-
Y given X? Y given X?
No, sir, I was just having a doubt if the other order is that of any importance. Like, does that have any significance in the real world? Basically, P of X
Oh yeah,
given.
yeah, a lot of significance it has. Okay, that is called the class conditional density. This is called the conditional of labels given data. That is the conditional of data given labels, right?
Right.
So it does have a significance. I will see that. We'll see that. So I am setting up the problem of supervised machine learning now. So when we talk of unsupervised machine learning, we'll see that that has a significance. Okay.
Okay, sir.
Any other question? Yeah, Karthik.
Sir, yeah, I had a query. I mean, like here, always we are talking about predicting one variable given the other. So this label be should it be always something like discrete, or can it
Not
be like?
necessarily, no. Not necessarily. See, if you have y belonging to some y is another continuous random variable, you can evaluate the density of that at a conditioned on another random variable as well. In that case, the problem's name changes, no? Then it is called the regression problem. That's all. The difference between the regression and classification is that what sort of random variable your y is. If your y is discrete random variable, then the problem is called the classification problem. Then if y is a continuous random variable, it's called the regression problem. But the underlying task is the same. The underlying task is still to evaluate the conditionals of y given x fixed at a particular point. Okay.
Thank you.
Okay, we'll write that maybe, right? If y is discrete, it's the classification problem. If y is continuous, problem is called a regression problem. Okay. Okay. Now let's get back to what we were doing. So now given D, that is pairs like this, is sampled from the underlying joint distribution. Okay. Now given this, this becomes okay in good notes when I used to write put a box like that. No, that will become a nice box, a rectangle. Here it doesn't. Okay. Okay, so this is the central problem in this is what is called as supervised machine learning. Supervised machine learning, or also called as the discriminative machine learning, discriminative modeling or machine learning, whatever. Okay, you understand? So now given data from the joint distribution, I want to estimate the conditional density function of y given x. Is this okay? Be it classification, be it regression, this is the problem that we are solving. Questions on this? See, note that we don't know the density function P of y given x. Okay, we only have samples drawn from the joint distribution of x and y. So now, given having samples from the joint distribution of x and y, how do you estimate the conditional distribution or conditional density function is a question that is to be answered, and that is the question that is answered in all of like discriminative machine learning. Okay, we will see that a part of it now, but this is the problem setting of discriminative machine learning. Now you can now see the connect, right? So now oh, just went is there a way I can put a box, nicer box? Try.
There seems to be circle and a square icon at the top. Left.
Here.
Third one.
This one.
Third from left.
From left. Third.
Sorry, third from right. My mistake.
Shapes. This is okay. Okay. Now, yeah. So now, how do you estimate the conditional distribution, conditional density function given data from an unknown distribution is a question. Okay. So maybe write this also, no, with px is unknown here. Okay. It's a question that we'll answer, but this is what the machine learning problem is all about. Okay. Discriminative machine learning is all about that. So now this xi can be okay. So let me write. So xi is in some RD, right? And yi can be discrete 1 to k, or it can be another rk. Okay. If it's this, then it is classification. If it is this, then it is regression. All right. Entire supervised machine learning is this. That's all, right? How do you estimate this P of I given X given D? Now, what about the so-called generative models and unsupervised machine learning is that you have given, I mean, in my mind, both of them are very, very similar. Given D that are of this form, so you don't have the notion of Y there. Okay, so you estimate Px, that's all. There is one other part to the generative problem. Maybe I'll write to estimate Px and sample from it. See, I have to define what sampling is. Shall I do it now or later? Because it is little digression. Okay, let me define it perhaps. Before I define the problem of generative modeling, right, I would like to ask you this question. Any questions on this definition of supervised machine learning? See, I still have not answered this question of how do you estimate the underlying density function. I mean, that is what we are going to do with this entire course. But problem setting, I want you people to understand what the problem setting is. Yeah, so is the problem setting clear for discriminative modeling and supervised machine learning? Please let me know if you have questions. Karthik?
Sir, one query. I know we don't know the distribution function P of xy, but how do we know that it's all been sampled from that distribution function itself? I mean,
That's an assumption that we make.
okay, so
We
there
make an
can
assumption that the data is coming from one given distribution. Have you heard of something called IID?
sorry, sir.
Independent and identically distributed data, IID data. Have
No,
you heard
sir.
of that
Yes,
term?
sir. Yes. In
Yeah,
random
that
process.
actually means, yeah, in fact, I deliberately left that because I didn't want to confuse you with things, but yeah, let me tell you this. So this actually sampled IID from this distribution is what is said. This means that they are independently and identically distributed. Identically distributed means that all of these are actually coming from the same distribution. The independence means that all of these data points are independently sampled, which means that observing one image is independent to observing the other image, the next image. Is that okay? So now we make basically we are making an assumption that the entire data is coming from one distribution. That is why all these methods that have been developed using the IID assumptions fail if there is a distributional shift.
Okay.
Right? That's
Yeah.
because there's suddenly the IID assumption gets broken, which means that the data that you have given was coming from one distribution and you modeled it, you did everything. Now the test data comes from some other distribution. What do you do? Right? So that is an assumption that we make that the underlying distribution stays the same. Okay. Yeah, Aditya.
Sir, I wanted to ask, what about outliers in that scenario? Like we assume that there are no outliers then?
No, I've not defined what an outlier is, right? See, even if it's an outlier, it can still come from the same underlying distribution with less probabilities, right?
Okay.
Isn't it?
Yeah.
It can come from the tail of the distribution, but it is still coming from the same distribution, is it? Right?
Yeah.
Okay. Okay. If there are no questions, any more questions on this? If not, we'll move on. I'll define what generative modeling is. See, generative modeling again that you are given data that is sampled IID from an unknown underlying distribution. This is also unknown. Okay. Now again, you still want to estimate the likelihood or the density function. That's also same. One additional thing that comes in the generative modeling thing is you need to sample from it. Okay. So now what do you mean by sampling? First, let us put a box around it. This is the problem of generative modeling. Okay, this is generative modeling. So given data from an unknown, drawn from an unknown distribution, estimate the distribution or the density or corresponding density function and sample from it. Now sampling is defined as follows. The process of sampling is that we need to implicitly conduct or let's say run the random trial corresponding to the sample space. This is the process of sampling. Now you understand what I'm meaning. So let's say that your sample space is tossing a coin, right? And you are given some 100 coin tosses. Now what do you mean by sampling? You have to implicitly toss the coin again. See, in practice, we'll not have the coin and wherewithal, right? So, but what we can do is once, why am I saying implicitly is because if you run the underlying random trial again, what you get is an outcome. But now, because we are working in the space of random variables, we will get one point. So, this implies that sampling leads to a point in the range space of the random variable. Do you see why? Do you all see why? Because see what we are doing is sampling is conducting the random trial that gave rise to the sample space, right? So once you conduct the random trial, you have an outcome. And once you have an outcome, you know the entire story, right? You have the random variable, and because you have the random variable, you get a point in the range space of the random variable because random variable operates on outcomes and gives you a point in RD. Is this clear? Now, generative modeling is all about this. Okay, I'll take questions. I'll take questions. Generative modeling is all about this, that you are given some data, okay, that is drawn from an unknown distribution. Okay, you should, of course, estimate the underlying distribution. That is a part of the process. Not only estimate the underlying distribution, unlike in the discriminative learning case, you should also learn to sample from it. Now, what do you mean by learning to sample from it? Learning to sample from it is simply you are conducting the underlying random trial, right? Again and again, so that every time you conduct a random trial, you have the random variable that is there, which will give you a point in the range space of the random variable. That's what. That is generative model. That is generative sampling or generative modeling. Okay, all this chat GPT, right? All the everything that you see, Sonnet, Claude, etc., are actually doing this. They're actually running the underlying random trial multiple times whenever you do an inference. Okay. Now, somebody asked me a question just now, right? They said that, okay, what is the significance of x given y? Okay, so that is actually that distribution. If you learn to sample, estimate p of x given y and learn to sample from it, you are actually learning to sample from the conditional distribution. Sampling from conditional distribution is nothing but conditional generation or prompt-based generation. So you're given an input prompt, right, which is represented as another random variable y. Now p of x given y is the distribution that you're sampling from. Given a particular prompt, okay, y is fixed at something, you need to learn to sample from px. So it is p of x given y is what you sample from in conditional generative models. This is unconditional generative modeling, where given data are drawn from an unknown distribution, you estimate the distribution and learn to sample from it. Sampling is the process of running the underlying random trial, okay, so that you get an outcome from the sample space, and because you have a random variable that's already in place, instead of observing the outcome, what you observe is the element in the range space of the random variable. Practically speaking, if you are given some images, all the images are points in the range space of the random variable. If you learn a generative model on it, if you get a generative model on it and learn to sample from it, when you sample, what you get is another image, okay, which is nothing but a point in the range space of the underlying random variable. And you will have to sample. See, also observe that is a very important point here in the definition, that I say that you have to run the random trial that is corresponding to the underlying sample space. You see, it is not doing. See, if you are given a, let's say that you are given a coin tosses from a biased coin. Okay, it's not enough if you just learn to toss a coin. You have to learn to toss a coin, toss that particular coin which generated this random trial, isn't it? Do you understand what I'm saying? So the sampling has to uh, respect the underlying sample space, which means that it has to respect the underlying probability measure, which also means that it has to sample in accordance to the underlying distribution. Okay, so let me complete it perhaps. Sampling leads to a point in the range space of the random variable respecting the underlying distribution. Right? This means that if I have given you data from MNIST data set, the sampling has to generate data from MNIST data set only. No, it should not start generating data from some other human faces or something. It has to generate data from MNIST data set. What is the mathematical way of saying it? That you run the corresponding random trial, right? That would respect the underlying sample space, which means that the underlying probability measure is intact, which means that the underlying distribution function is also intact. So now you understand, right? Now you understand why there is a connect between estimating px and sampling from it. If you estimate px, you can't sample from an unknown distribution unless you estimate the underlying distribution, because you need to sample such that the underlying distribution is preserved. Do you see that? So now the entire problem of generative modeling is that you are given data that are drawn from an unknown underlying distribution. Learn to run the underlying, random trials, okay, such that the distribution function is respected and intact. That's all. So if I say that you will have to sample such that you have to sample from the underlying sample space, it is understood, no? Because you can't sample from the same sample space unless the measure that is there is preserved. But yeah, I'm just making it explicit to say that you'll have to learn to run the random trial such that the underlying distribution is intact, which means that you better estimate the underlying distribution and then you learn to sample from it. So this is the difference between the discriminative modeling and generative modeling. In discriminative modeling, what you do is you stop at estimating the conditional distributions of the labels given data, given X, right? Here, you estimate the distribution and also learn to sample from it. Okay. Okay, questions. Arijit?
Maybe sir, I did not understand it fully because generative model we need to know how to sample from it, right? So suppose we took this coin example, we already sampled the coins, right? Maybe there are 100 coins, and out of that we are choosing 10.
No. Hold on. No.
Okay.
In the coin toss example, we have one coin. We don't have 100 coins.
Okay.
We have tossed one coin 100 times. That is your data.
Okay. Got it.
But you don't know what is the likelihood with which the coin turns out to be head or tail. You get it?
Yes.
Okay. Learning to sample from it is to learn to toss the coin again without having access to the coin.
Okay. Got
right?
it.
So we have, we have not sampled yet. We only have samples that somebody has already given us. That is our data.
Okay.
So without having access to the coin, we need to know how the coin would have turned out when if we toss 10,000 more times. That is sampling.
So it basically means we have to sample more from near the peaks of the PDF function.
No, I'm not saying peak. You just have to sample it such that the underlying distribution function is intact. You can sample from the tail also.
Yeah,
You should
occasionally from
sample
the
from the
tail,
tail.
but more
I
from
mean,
the.
no, please see. You simply say that you sample such that the underlying distribution function is respected. That's all.
Okay.
See, if you are sampling from so-called tail, the measure associated with that outcome has to be lesser. That's all it means.
Okay.
You get it? See, now that you know this language, try to use this more. So basically, I'm saying that the underlying measure is respected. Now, if the measure has to be respected, then the underlying probability measure, or if the distribution has to be respected, then when you sample 100 times, right? Like more number of times. If there is an outcome that has more probability, then that has to appear more compared to other, right? Obviously.
Yes.
But the underlying measure has to be perfectly intact. Otherwise, then you are not running the correct random trial. No, you are learning to sample from some other random trial or some other sample space which is undesirable.
Okay.
See, that is what hallucination is all about, right? See, what is hallucination? That the underlying distribution is not estimated properly. If it's not estimated properly, it will start sampling from some other sample space that does not correspond to the given data.
Okay.
But sir, there is no guarantee to, entirely we can reduce this hallucination, right?
That is what I'm saying. No, that is why the entire course is designed that you need to, that depends on how good is your estimate on PXS. Isn't it? So now the sampling process has to estimate the underlying distribution. If you have not estimated the underlying distribution correctly, then you will obviously when you sample, you will get the things from outside of the sample space, no? So that is why you have so many techniques. You have that model, this model. Every model is trying to do the same thing. That every generative model, right? Be it GPT, autoregressive, GPT, etc., come from this family of models called autoregressive models, right? And there is this adversarial networks and diffusion models and flow-based models, score-based models. All of these are trying to solve this exact same problem, that they are trying to estimate the underlying distribution and trying to sample from it. Why are there so many models? Is because each of them estimate the underlying distribution in a different way. Since they don't estimate the distributions quote unquote perfectly, you have so many models. Same thing goes for the discriminative models also. Why do you have linear regression, logistic regression, and SVMs and kernel machines and neural networks? All of them are actually trying to solve this exact same problem, which is estimating the underlying conditional distribution. But one model is better than the other because different, they estimate the underlying distribution in a different way. Okay. Now you might have heard this term, no? All models are wrong, some are useful. Right? So everything is a model, everything is trying to estimate some distribution given some data. They're all models, all of them are wrong. Some of them are useful. That is why you have metrics to estimate how good the performance of a given model is. Okay, so now I have to define what is a model, right? Observe that we are solving an estimation problem. We are trying to estimate a density function. So every estimator is a model. When we say that we are looking at generative models, discriminative models, what is a model? Model is nothing but an estimator for the underlying density function that we want to estimate. There can be thousands of estimators. Each estimator comes with its own property. Right? Claude has its property. Sonnet has its property. Gemma has its property. This thing, GPT has its property, and so on. Everything is a model, but all of them are trying to do this exact same thing. That given data from an unknown distribution, trying to estimate the underlying distribution and learning to sample from it. Okay. Yeah, Raghavendra.
Yes, so just to clarify my understanding on this prompt-based generation. So you mentioned that that problem is basically to sample from P of X given Y. Is that correct?
Correct. It is
Okay.
estimating the conditional distribution of X given Y and learning to sample from it. See,
Okay,
we
thank
will
you.
see this in great detail. In fact, we will look at multiple estimators in this course. Okay. Yeah. So this is, I'm just setting up the problem now. Okay.
Yeah, thank you.
Yeah. Astik.
Hi sir. So here
Just a
the
second. Just a second. Like I'm both happy and a little disappointed. I'm happy that more people are talking. I'm slightly disappointed that the same set of people are kind of asking questions. I mean, I'm not discouraging you people, but I want to encourage the entire class to participate. Okay, so feel free to ask questions. Otherwise, yeah, I mean, I don't want to go into the philosophy of pedagogy, but yeah, I encourage all of you to ask questions. Don't hesitate. To ask questions. Okay, Astik, go on.
yeah, so as we discussed that we are estimating the distribution, but we are estimating the distribution via the density function associated to it, right?
Correct. Yes.
Yeah,
Correct.
so earlier we discussed that the density function can't be like a proper like exactly 100% representation of the distribution function. So whatever we do.
No. Hold on. No. I didn't say that. Yeah, I didn't say that. I said that density functions do not evaluating the density functions don't give you probabilities. That's all.
Okay.
Okay. But
Mm-hmm.
density functions and distribution function has a one-to-one mapping to it. If you estimate the density function, then you know distribution function and vice versa. If the density functions exist.
Okay, so if we get a value of a density function at a
Then we
particular
know
point.
everything about the distribution function, because
Okay.
if you have the density function, right, you can integrate that and get the distribution function.
Okay.
Right. See, but somebody asked me that question. No, why do we work with density functions and not with distribution functions? Is because
Yeah.
computationally easy. That's all.
Yeah.
Otherwise, I can actually say this. No, the problem is I can set the problem as estimating the underlying distribution function.
Okay.
Right. But I set it up as density function because when what happened? Yeah, I set it up as density function because when I answer this question of estimators, no, I will use density functions for everything. That is why. But yeah, so there is a one-to-one correspondence between density function and distribution function. Just that evaluating the density function at a point will not give you a probability. That's all. Yeah.
Okay. Understood. Yeah.
Oh, sir, just to continue that discussion. So here we said that we will get the likelihood, right? And the likelihood may be low, but still the probability may be high. That is possible, right?
No. See, again, when you evaluate the density function at a point, you get a likelihood. So for continuous random variables, there is nothing called probability at a point. That itself is not defined.
Okay.
Isn't it?
Yes.
Because probabilities are evaluating the distribution function. Now, if you evaluate the density function at a point, right, you get 0, which means that, I mean, so rather if you integrate the density function, right, at a particular point, you get 0. So the probability of obtaining a particular image is 0, actually.
Yes, that's correct. But
Yeah,
what
that
we
is
are
why we work
interested
with
in is,
likelihoods.
yeah, but what we are interested in is the probability, right? That,
No.
I mean, when the probability is high, we want to take that particular label
No,
as
just say, see, no, for you mean the discriminative part you're saying, is it? Not the.
Yes, for the
Yeah, see,
discriminative part.
if y happens to be a discrete random variable, then density functions are probabilities.
Yes.
Because they are mass functions.
Okay.
Right?
But if it is a regression problem, then?
If it's a regression problem, then you should just say that it's likelihood. I want a point with higher likelihood. Don't call it probabilities, that's all. You see?
Yeah, but that's my point. So higher likelihood may not mean the higher probability, right?
Probability of a point itself is not well defined. It is not even defined. So you take decision based on likelihood is all I'm saying. Stop there. See, don't jump to the probabilities, because probabilities of continuous random evaluating the density function at a point or likelihood of a point is not the probability of that point.
Yes.
You get it?
Yeah.
Yeah. So just say that I want to pick a point with higher likelihood. That's all. That is perfectly fine. Don't say that higher likelihood corresponds to higher probability. That is incorrect.
Okay. Yeah.
Yeah. I mean, I'm just making it pedantically correct. They're nitty-gritties, but that is what it is. Yeah.
Yeah. Thank you, sir.
Okay. See, now you should see the connect between estimating the density function and sampling from it, right? I mean, if you can't estimate the density function, you can't sample from it, because you have to sample in accordance with the underlying density function. That will happen only if you know what the density function is, right? Yeah. Okay. Aviroop?
Yeah, so my question is that you have defined generative modeling and discriminative modeling, where in discriminative modeling you have explained the relation of uh, supervised machine learning. So do we have a corresponding definition for unsupervised learning also? I'm just asking for clarity. Yeah.
Yes. Yes. So you can also call generative modeling as unsupervised machine learning. Okay.
Okay.
Yeah. So there is yeah. For now, let us call in unsupervised machine learning. Not all unsupervised machine learning models enable sampling. No, for instance, if you do k-means clustering, right, it will not enable sampling, strictly speaking. But if you do, if you do GMM clustering, it does enable generative modeling. Okay, and also k-means happens to be a special case of GMM. You For now, let us call this as unsupervised machine learning. But when we come to this thing called latent variable models, right, which is a special case of special way of modeling the underlying density function, then that also is called unsupervised machine learning. Okay, but yeah, so for now you can assume that unsupervised modeling, let's say that unsupervised models are sort of subset of generative modeling. Okay, for now.
Okay. Thank you.
Maybe I'll not write it. Let's simply confuse it. Yeah. Was this Sushil? No, this was Aviroop, I suppose. Hello?
Yes, thank you, sir.
So we still have a question. I think Sushil, you have a question? Sushil? Okay, so maybe he's not there. Okay, so let us move on. Shall we move on? Any other question? Okay, so let us now ask this. Yeah, Manish, go on.
Sir, you are saying that it's a unsupervised problem, but we in generative model also, like for suppose text based, we try to predict the next word, right? So while training, we fed that next word, what will be the next word, tried to predict that. So it's a kind of supervised only, in that case.
Yeah, it is not, because your I mean the word is the word is modeled as X here. Okay, in that case, when you're looking at autoregressive models, your words are also the random variable X. So now you are actually sampling from the underlying distribution. See, that is why I define prediction in this case particularly as evaluating the likelihood at a point. There's no supervision per se there. See, that is why I don't want to use this terminology of supervised and unsupervised learning, precisely because of this. The line is very, very blurred. You simply say that in both the cases you are estimating some distribution, okay, given some data. That is all. Okay, but typically in supervised models or discriminative models, you will not have an explicit sampling process, but in generative model, you will have explicit generative sampling process. That's all. Okay. So maybe let us call this as discriminative machine learning if you are more comfortable with this. Okay. Discriminative modeling and generative modeling. Discriminative modeling does not have sampling. Generative modeling has sampling. So let's have that as the difference. Yeah, Sushil?
Okay.
Now the important question is,
Sir, one question.
yeah, go on.
What if, like in both the cases, we get the density function P y given, like in one, like for the discriminative model, we get the density function. So why can't we get the distribution function from that?
We can. I'm not saying we can't. We can. But I mean, most of the applications, right? It is enough if you have the density function. We can get the discriminate. We can get the distribution function from it.
Okay, and then like if we want to sample it from, like do sampling from that, like for an example, we have a set of images of 10 classes, basically 10 different animals, and we get the underlying probability distribution. And then we sample and say, okay, we want to generate an image of an animal in a different scenario. Let's say we had the sample of animals in jungle, but we want that to want the model to generate the images for those animals in a city context. So won't that be considered as generative model?
That is a generative model, but the is changing, no? See, that is all. I mean, that is definitely generative model. But then, see, if you only have images of animals that are from like jungle in your data, then there is no way that your model is generating images of animals in cities.
No, sir. My point was, so in the discriminative model, we have the like basically the K classes from which the data belongs. The data can be classified into. Now, using this available data, we develop like we get the distribution, and we develop a model to generate some fresh data, fresh data out of it.
See, when we say that, see, that is what I'm saying. Let me, I don't know, maybe I didn't convey the point properly. See, when I say that you need to sample from the corresponding underlying distribution, it means that you have to sample from, you have to get a quote unquote fresh sample only. You know, sampling is always fresh sampling. Right? Suppose you are given 100 images of these animals. Let them belong to 10 different categories. When you generate, you have to generate it from those 10 different categories only. You can't generate from an unseen category, is what I'm trying to say.
Yes, sir. Agreed.
You can't generate it by construction because you have only estimated the underlying distribution.
Correct.
That's all. When your model is as good as your data, unless your model has seen that, see, it can generate the images from, which are not there in your data set.
Correct.
You understand? But it can't generate data from the distribution that does not correspond to your data set.
Got it, sir.
You understand that? See, for example, if you have, let's say, the images of human beings as your data, when you construct a generative model and sample from it, it will generate the face of a non-existent human being. Okay? But it can't generate the face of a monkey or a dog or a cat.
Correct, sir. Agreed.
That's all. That's all. That is what is meant by respecting the underlying distribution.
Got it, sir. So, like my point of making this statement here was whether we have the classification or not, it won't make a difference, right?
Yeah, it should not. But as I said, There is this thing called conditional generation that I've not talked of, right? Where you learn to sample from P of y given x. Sorry, P of x given y. Now suppose you have 10 categories and you want to, let's say that you have cat images, dog images, whatever images, and you have learned to. The question is, what is the underlying distribution that you are modeling? If you are modeling, remember that when I said that there is a conditional distribution, it means that you are modeling y equal to a particular value, right? Now let's say that y equal to 1 corresponds to cats. If you are modeling this distribution, learning to sample from it, you are only learning to sample from the cat images.
Yes, sir.
You understand? However, if I just take this and multiply this with py and just take a sum of all this, what am I doing? This is equal to px, isn't it?
Yes, sir.
Now, if I combine all the images from different categories and learn to estimate this distribution, px, then I am sampling from all possible animal faces. That's all. So it depends on what distribution are you modeling. You get it?
Yes, sir.
See that those categories or those labels are random, or I mean I should not be using this word random. They are synthetic, or they are pseudo, in the sense that, see, if you can group all the cat images into one and call that as one distribution and estimate it, so that when you sample you only get cat images.
Yes, sir.
If you take, say, images from 10 categories, combine them all and call them px, and if you estimate that, then you get images from all categories. That's all. So
Got
that
it, sir.
categorization is a sort of, it's a synthetic thing, right? Depends on like what are you calling as the underlying distribution and data. That's all, right?
Okay, sir. Okay, sir.
Okay. Yeah, Manisha.
Sir, as an extension to this discussion, and we have answered that, but so basically what we are saying is we are finding the, as a part one of the problem, it's finding the distribution, the underlying distribution, which will tell us which class is linked to which label in a way.
No, hold on. See, in generative modeling, we are actually not bothered about which data point is associated with what label, because there is no idea of labels here. See, estimating the underlying distribution simply tells you that what is the likelihood of this particular image under the given distribution. That's all. So there is no idea of class here at all in generative modeling. You get it?
Yes. So, but we still, the first step is to find the underlying distribution, right?
Correct.
Of what all are the, like, for example, what was being discussed for all the animals. We are kind of it's kind of which is
No. It's a strict no. I tell you. See, you have to understand what is meant by estimating the distribution in the generative modeling case. And we will see examples and we will actually go deep into it. But anyway, at this step, you need to understand it. See, if you are given, let's say, 100 images of animals, okay, estimating the underlying distribution means that you are trying to find out how likely, or what is the likelihood of a particular image under the distribution. That's all. How likely is that I'm obtaining this image? Suppose I'm conducting that random trial. How likely it is to obtain this particular image is what I'm finding by estimating the distribution. It has nothing to do with classes. Here, there is not even an idea of classes because there is no y here.
Okay.
The way I have set up the problem, there is no y here at all.
Okay, get that. Okay, so it's just the likelihood of getting a particular point in that distribution, basically.
That's all. So if you have 1,000 images, I'm just calculating what is the likelihood of obtaining this particular image. That's all.
Okay, right.
See,
right.
if you imagine obtaining an image as a roll of a die, okay. So what I'm asking is, when I conduct that random experiment, okay, what is the likelihood that I'm obtaining this particular image? That is what estimating PX is all about. So what is the likelihood that I get this particular face? That's all. I mean, face of the die. I mean, if you take the die example, there is no notion of labels in this setting.
And then the sampling part that we are talking about is basically from
is that you are obtaining a new non-existent human face. That's all. You are actually obtaining an image. That is sampling.
Getting that. Yeah, I think I get the notion of that. Yeah, right, sir.
Right. There are two things here. One, see, once you estimate the underlying distribution, you can plug in any of the data points that are within your D or outside of your D, as long as it is coming from PX, and estimate the likelihood of that particular point using this PX.
Absolutely. Yeah.
Sampling is that you are obtaining or you are running the underlying random trial so that you get a point, a fresh or a new point that is not a part of your D, but still comes from the underlying sample space. That is sampling.
Get that, sir. Yeah.
So there is no notion of labels here at all.
Yeah. Got it. Got it. Right, sir.
Right. So now I still have not defined this conditional sampling, right? I mean, sampling from P of X given Y. See, as I said, see, as I said, this has a notion of, prompting.
Yeah, you want to know what kind of prompting is, like you are asking the question like this category, and what is the image that I'll get probably for this particular category or so.
Exactly. So that I have not brought that notion yet. I mean, see, now because that is simply confused stuff. Once you assimilate this idea of generative modeling and sampling, putting a conditioning here and saying that I'm modeling the conditional distribution is not difficult.
Right. So that was my point also. So that doesn't seem difficult, but now I think I get the actual problem there. Yeah.
See, yeah. So it is not estimating Y given X. You should understand that. The problem in generative modeling is not estimating Y given X. So that is the problem of discriminative modeling, that you are estimating P of Y given X. And there is no sampling here. Okay. But in generative modeling, the two things. One, there is no notion of labels here. Okay. And two, you need to learn to sample from it. I mean, that's a huge thing because see, suppose you are given MNIST data set and you create a CNN to predict the classes, right? That will not give you samples from MNIST data set, does it?
No.
That is simply estimating P of Y given X. Right? But if you build a GAN or a diffusion model on MNIST data set, it will give you new samples from the MNIST data set that are unseen, because you are not only estimating the underlying distribution, but you are also learning to sample from it. That is generative modeling. What is common in both the cases is that there is some distribution that has, there is some sample space and some random trial that has happened, and you have generated the data already. And that is the input to both all of machine learning, that you have some data given from an unknown distribution. Now, what do you do with it is the question. Having that data, if you estimate, if your data is of this sort, if you rather model your data coming from a pair of random variables having the joint distribution, and you interpret one random variable as data, or rather the features, and the other random variable as labels, then if the problem is set up as estimating the conditional of the label random variable conditioned on the feature random variable, that is discriminative modeling without bothering about sampling. But now, okay, I'll make things a little involved because you asked this question. Please see if you can understand this. See, I can actually construct a generative modeling having the data that is given in discriminative modeling as well. Do you see? What I am trying to say is, suppose I have the data set of animals with the corresponding classes also given, right? Now, if I estimate Pxy, the joint distribution Pxy, and learn to sample from P of X given Y, then that is another generative modeling. That is conditional generation.
Get it. So that's the joint distribution here, and we also get it from a single, distribution of a random variable.
Distribution of a single random variable. It depends on how do you want to view your data. See, if you are given 1,000 animal images, now, do you want to categorize them into subcategories and say that, hey, look, my data is such that I have the image and a corresponding label with it? Or do you want to see that as simply 1000 images without having labels?
Yes, and then draw sample.
That's all. See, yeah, that's all. It's a modeling choice. What are you drawing samples from? Are you drawing samples from Px, or are you drawing samples from Px given y? Right? Now, if you are drawing samples from P of x given y, it simply means that given these animal images and the fact that I want to generate from dog images, or rather I want to generate the image of a dog, then I know how to do it. But now if I mean that needs the corresponding labels as well, right? Because you have to estimate P of x given y. But I mean, estimating P of x given y and learning to sample from it also is a generative model, right? So suppose you estimate P of x given y and sample from x given y, that's also generative modeling. That is actually conditional generation, which is what ChatGPT does. So given y, which is a particular prompt, you want to generate. And for that, the kind of data that you need is pairs of x comma y. Do you see that? Because you need the underlying joint distribution.
Absolutely, yeah.
Right? So it depends on like what sort of data you have and what sort of density are you modeling and sampling from. That's all. But the major difference between these two models is that in discriminative modeling, see in both of the cases, you have data drawn from an unknown distribution, you are estimating some distribution. But what is not there in discriminative modeling is that you don't learn to sample. But in generative modeling, you learn to sample from it. That's the only difference. Right?
I get it now.
Okay. I hope that this notion is clear because I mean this is what differentiates let's say a ResNet based CNN or a VGG net from a diffusion model or a GAN. Both of them are actually estimating the underlying distribution given data. Both of them are given same kind of data. What is different is that the generative models learn to sample from the underlying distribution. Discriminative models don't learn to sample. That's the difference. Yeah.
Right, sir.
Okay, great. Any other question on this? I mean, this is important because this is, I mean, if you understand what the actual problem is, then rest of the math and algebra becomes easier. Any other questions? So now you see that, right? I mean, now one of the central problems in both in discriminative and generative learning modeling is that given data from an unknown distribution, how do you estimate the underlying density function is the question, right? This is an important question, right? Given data drawn from an unknown distribution, how to estimate the underlying density function is the question that has to be answered. Okay. For that, there are multiple techniques. One technique that we will be seeing, I mean, that is common across multiple models that we will see in this course is what is called as divergence minimization. See, all these models, right? GANs, VAEs, diffusion models, autoregressive models, etc. All of them employ this technique called divergence minimization to answer the above question. And by the way, every generative model that you can think of, right, that the people are coming up with are actually solving this problem that given D, you estimate the underlying density and sample from it, right? Minor modifications here and there. I mean, depends on what sort of D that people have. If you have like text and the corresponding next word or label or something, image and label, you learn to sample, estimate the conditional distribution and sample from it. That does not matter because that's simply a like a design choice. But they are all solving this particular problem. Now, to solve this problem, you need to estimate the underlying density, right? Otherwise, how do you learn to sample according to that particular density? So you have to estimate the underlying density. So all of the generative models, in fact, even discriminative models have to solve this problem of divergence minimization, or rather, given data drawn from an unknown distribution, how to estimate the underlying density function is a problem that all ML models have to solve. And one technique to do that is what is called as divergence minimization that is employed by all the existing generative models. Okay? So we will see that next, how to, and what is this divergence minimization and how to use that to solve this problem is something that we will see next. Shall we take a break now? I think it's 90 minutes. Let's take a break for 15 minutes now. Shall we? Okay. So in my clock, it is 11 a.m. Let us reconvene by 11:15-ish. Okay. Yeah. See you in 15 minutes. Bye. Hello, will we resume?
Yes, sir, sure.
So, okay. See, Chandan has just put a poll for tutorial timings, so please respond to that. It is, I think, both on WhatsApp and Teams. WhatsApp, I definitely saw it now. I don't know if it's on Teams. Is it on Teams already or?
Yes,
It
sir.
is there on
I
Teams
can.
also.
Okay. Please respond. Depending upon your response, whatever works for most of us, most of you will take that time. Okay. Okay. Let us continue. Yeah. See, one small request is that from now on, the content will become a little dense and intense. So please spend some time after the class in sort of just looking at what is happening so that the storyline is not lost. Okay. Uh, so please do that before coming to every class, and also you can look at my reference, look at my notes that I have given to you. That also has some references. Okay. So now, what is the question that we are looking at? That we are given data drawn from an unknown distribution, and we want to estimate the underlying density function. That is the question that we are looking at. How do we do that? One of the methods to do it is via this thing called divergence minimization. So what is the idea there? Okay, the idea is the basic idea is the following: that first assume a parametric form for the unknown density, for the density function that is to be estimated. Okay, for the density function to be estimated. Okay, so I mean, this will give you step by step. So this is the first step. Now, what does this mean? This means that so now you are given some data D, right? You assume that the density function that I have to estimate uh, can be represented using a neural network with some parameters. You understand? Okay, so typically denoted by denoted with p theta, okay, where theta are the set of parameters. Do you understand what this means? So an example can be multiple examples. Assume your p theta. Let's say that I assume it to be a Gaussian density, and note that this density function is still on the same sample space or the random variable as the underlying data, right? I mean, obviously it has to be defined on that only. So this can be, let's say, a Gaussian distribution, okay, uh, with some mean, okay, mu and some variance sigma. Now theta in this case happens to be the mean vector and the variance matrix. You understand? So what we do is we assume a parametric form for the density function that is to be estimated, okay, denoted by p theta. You can assume that to be anything. You assume it to be a Gaussian density, assume it to be exponential density, and those parameters happens to be that. That is one example. The other example can be that I assume it to be a neural network, right? So p theta of x, right, is output of some neural network, right, where g theta is a neural network. and this Z is simply some Gaussian distribution. So basically the way I'm modeling this is there is a sample of the Gaussian distribution that is going through a neural network G theta. We will go to the details of all this in a while, but these are examples. So Z is going as output, and what am I getting at the output are actually P theta of X. Right? I can model it. I mean, this is again a design choice. This is where different models are different. So this d theta can be a transformer, right? It can be a CNN or RNN or whatever, depending upon what your choice is. But basically, the idea is that you assume a parametric form for the underlying density function that is to be estimated, denote it by p theta. Is this clear? Like, what do I mean by parametric assumption? So this is the first thing that you do. So once you make that assumption, what is the second step? The second step is that define and compute okay, a distance or a divergence metric between okay, the true density function. It's actually true density function, which is px, right? And assume parametric density. Parametric function p theta. Okay, so basically metric D, okay, that would take the true density and the parametric density. This is the notation, okay, px double slash p theta. So this measures far close r. So different divergence metric that would compare the true density function to the parametric density function. You might ask me here, right? I mean, we don't know the true density function. How do we compute this? Hold on to that question. That actually turns out to be the central question of all generative models. When you don't have the true density function, how do you estimate the distance metric is a question that we'll answer later. However, what we need to do is we need to define and compute some sort of a divergence or a distance metric between density pairs of density functions. In this case, the density functions happens to be the true density and the parametric density that we have assumed. Okay. Okay. Once we do that, what do we do? So adjust or compute the parameters of p theta such that d of px slash p theta is minimized. This procedure, right? This is what is called as training a model or learning a model and so on. This is the learning part of it. Understand, mathematically speaking, what you do is you set the parameters theta star, okay, as the ones that would minimize. So what do you mean by R min? The set of parameters that would minimize a function, okay? Now that would minimize the distance metric that you have defined between density functions. You have two density functions. This entire thing now will become a function of theta because p theta is a function of theta. And you want to solve an optimization problem over the space of theta such that this distance metric is minimized. Now the final estimate this is the learning problem. This is the training or learning of generative model, right? Training. Learning. So training basically is solving an optimization problem. You all know that, right? That is why we use gradient descent and backpropagation algorithm to train. Okay, basically you are solving an optimization problem. The final estimate for Px, right, is simply P theta star obtained by solving the following. P theta star obtained by solving the above optimization problem. Optimization is, in this case, it is the minimization problem. This is the general recipe, right, of how to solve any machine learning problem. It can be generative, discriminative or generative modeling. What are we doing? We are given data from an unknown distribution. We assume a parametric form for the density function to be estimated, typically denoted with parameters theta. See, that is why now you can, I think, relate. Now, in the discriminative case, the underlying density function that we need to estimate is P of y given x, isn't it? We either model this as a logistic regressor or we model this as that is our model P theta. What is a model? This parameter for the underlying density to be estimated, right? This actually P theta is what is called as a model. Okay? Be it in a generative model or a discriminative model, the parametric assumption that we are making on the underlying density function is what is called as a model. It can be a neural network, it can be anything, okay, any kind of parametric function. Then the problem of estimating the underlying distribution translates to estimating the parameters of the underlying model that we are assuming, right? That is also a density function. Okay, now how do you estimate the parameters of this density function is the question. For that, we need to first measure. Let's say that we fix one value for this mu and sigma. Let's say that our model is a Gaussian model, okay, and the only parameters that we need to estimate are mu and sigma. We initialize that with some value. Now you get one p theta with that. What we should do is we should compare that p theta with the actual density. Now for that, we need a way to compare density functions. If you take pairs of density functions, you need a way to compare the density functions, right? Now you compare that and you see if it's large. If the distance between the true density and the density function with a particular set of parameters is large, then you change your parameters in such a way that that distance become lesser. Right. So for that, you need to first compute a distance or a divergence metric between the true density and the assumed parametric density or the model. Okay. And then adjust or compute the parameters of the model such that this divergence or the distance metric between the pairs of density is minimized. That is what the training is. Mathematically speaking, you are solving this optimization problem that you find your theta such that this distance metric itself becomes a function of theta, right? Now you need to find this theta such that the distance between the px and that particular p theta is minimized. So we should solve this problem, which is training the model. The final estimate for px will be that p theta star. Theta star is the set of parameters that you have gotten from solving this optimization problem that would minimize the distance metric between the true density and the model density. Yeah, is this clear? Now, again, the open questions are, I have not told you two things. I have not told you how to compute this distance metric when you don't have px. We still don't have px, right? That is our whole problem. I have not told you that. I'll tell you that. The second thing that I have not told you is how to solve this optimization problem and what sort of model choices that we need to make. That will be the subject matter of this course, entire course. We will take different, for GANs makes, for instance, adversarial networks make some assumption on p theta. VAs make some other assumption on p theta. Diffusion models make some other assumption on p theta. They would change this underlying distance metric. They would change the way the optimization is being done. That is what the levers with which we can play. What sort of distance metric can we use? What sort of optimization can we do? What sort of model choices we can do are the questions answering in different models. But this recipe is going to stay. That you make an assumption on the unknown density function, define a divergence metric between the true density and the unknown density, and fix the parameters of the assumed density such that this distance metric between true density and unknown density is minimized. That is all the recipe is for the density. Not still told you how to sample. I'll tell you how different models sample in different ways. We will talk about it later. But this is how you estimate the unknown underlying density, and this is the recipe. Okay, this is called the divergence minimization, right? Because you're assuming a model, minimizing the divergence. And this D is called the divergence, and minimizing the divergence between the pair of densities. Okay. Okay. Any questions so far? Sanjit?
Sir, I wanted to understand what is this G of theta? When you have written G of theta, G theta
It's a
of
neural
Z.
network, no? I told you, no? It's a neural network. Simply a neural network.
Okay, and Z? Z
Is some random variable, some arbitrary random variable that will go as an input to this neural network. And whatever output this neural network is giving, I model it as P theta of X.
Sorry?
Whatever output that neural network is giving, no, I take that as P theta of X.
Okay, okay.
This is one way to model it. As I said, there are multiple models that one can think of, but this is one of the models that you can design.
Okay, sir.
Is that okay?
Yes, sir.
Yeah, so many questions. Karthik?
Hi, sir. I have a little, like maybe I didn't understand it fully about the parametric form that we were referring. Can we get it based on another example, maybe a little more simpler one? Why?
This
What
is
do
the
you mean
simplest
assume
one,
a
right?
parameter? Yeah.
Yeah, you assume if you assume that it's a Gaussian distribution, that's a parametric form.
Okay.
That how do you differentiate one Gaussian distribution from the other? Is through its parameters, no, mean and variance.
Yeah.
That's
okay.
all.
New
So
sigma.
you are assuming that it's a Gaussian density, but you don't know what the mean and sigma are. Correct? Now, how good is my assumption is a different question. It can be a totally crappy assumption that you have made. But that is I mean, that's why I said all models are wrong. No, you have made some model assumption. So these are simplistic models, but in places like GANs and GPTs, etc., these models are made expressive enough. They are made huge neural networks so that they can express a large family of functions. Basically, you're expressing the density function. Now you choose a parametric model such that it is expressive enough so that it can express a large family of functions. And transformers and neural networks are such functions. So now what differentiates one transformer from the other transformer is the weights that they have, right? Now that relates. Hold on. That relates. Suppose you have two transformers, okay, of the same architecture, but you have two underlying distributions you want to estimate, right? Using the same architecture, you can fix the weights of these two transformers in different ways, so that they represent two different distributions. That's all. That.
Okay.
In most of this course, right, our parametric models are neural networks only because they are expressive enough. Since neural networks are, I mean, we will see that neural networks are said to be universal function approximators. That means that you can use a neural network to approximate any function. That's a known result. Okay, that is why entire machine learning has moved towards neural networks, because they are very good parametric models that you can have a neural network and set its parameter to represent any function. Same thing goes for discriminative model also, right? Why did people move away from, initially people thought that, okay, this can be modeled using a simple logistic regressor. It was not expressive enough. What if the final density function that you need, okay, for the given data, that happens to be something that a logistic regressor cannot model? Then you need to go to more models that are more flexible. That's why the today's state of the art is that P of y given x. These the parametric family that you assume on the underlying density are neural networks or transformers or anything. Those models are expressive enough. That means that, see, no matter what you do, A Gaussian density can only represent this density, I mean, it can represent this, and all that. But it is a unimodal density with different, you only have 2 degrees of freedom to play with. What if your underlying density has something like this? A Gaussian density can never be right? No matter what mean and variance you play with. Now, that is why you need GMM can express this, of course, but right, I mean, you need more complex models to represent this, and that's why people use neural networks. Okay, so that's what is meant by parametric model, that you just assume that my real density is one member of this family, large family, that my parametric model can express. So basically, if I model that as a neural network or a transformer, I'm saying that my true density can be represented by one set of weights of this neural network. There exists one set of weights of this neural network that would represent my underlying density. And I'm interested in finding that one set of weights. Got it?
Got it. Yeah.
Now, how do I find that one set of weight is simply I fix a particular weight and I compute, I see how far my density that I have gotten from this particular weight is from my true density. And then I adjust my weight such that, that measure becomes lesser and lesser. That is training, no?
So yeah, a query here is when then we like try to minimize the particular variable that I understood. So if it is not
Divergence,
minimizing
not variables, call it divergence.
Yeah, divergence. So if I'm minimizing that divergence, say it is not minimizing up to my mark, will we need to go back and change the model again? I mean, like, is it what the neural
That's a good
network
question. Of course, you need to change. And that is why, you have like, ResNet 30, ResNet 50, ResNet 100. Why did people make it deeper and different kinds of architectures? Is because my divergence is not getting minimized.
Okay.
How do I know my divergence is not getting minimized? Is you through some metrics, evaluation metrics like, whatever, the accuracy, precision, etc. They are all surrogates to measure how bad is your divergence, right? If it's bad, then go back and change your model. That's all. It means that, okay, maybe the model assumption, the parametric model assumption that you have made is not good enough. Which if you are using neural networks as your parametric families, the architecture is not good enough. Change the architecture, make it deeper, have more neurons, have more hidden layers, etc.
So just to add on that point, just maybe a little bit philosophical question. I mean, like, what if it doesn't we can't model it using a parametric model at all? Maybe it's pure chaos kind of, where we can't find a one which satisfies our divergence values.
Then we are doomed.
Okay.
No, but it seems like all these transformers and billion parameter models are able to estimate the underlying divergence to a good level. No, that's why you have the boom of AI, right? I mean, they are working, which means that the divergence is minimizing.
Okay. Yeah. I was thinking, as you said, initial class, maybe change the math. Just
come again.
Yeah.
No, but I mean, if the nature, the mod, see this, all this probabilistic way of thinking has taken us this far. You see, we've actually reached pretty far. Huh? We have very, very strong models these days. Models that can crack International Mathematics Olympiad and get a silver medal. That's a very, very strong model, no? In model that can crack JE. I mean, we have such models. Good things are happening, right? So that's how people did research, right? I mean, what was all this research all about is that changing the speed theta, looking at different forms, changing divergence metrics, different divergence metrics, and changing the way this optimization problem is solved. That's only the 3 things that you can do, no? Either you can change the model assumption, or you change the divergence, or you change the way you optimize. That is all people have been doing so far.
Sure, sir. Yeah, I was thinking whether we like the parametric form itself, we can define a new one kind of. I mean, like, based on the inputs.
People have done that, no? I mean, like from MLPs, from logistic regressors, they went to MLPs. From MLPs, they went to CNNs and then RNNs and transformers, whatnot, and all these kinds of different model assumptions, right?
Okay. Thanks.
But the recipe itself has to be changed. This is By the way, this is also called divergence minimization or empirical risk minimization. People have tried to look at other ways of doing stuff as well, but the thing that has worked the most and one which is there in practice today is this. Okay.
Yeah, sure.
Right.
Thanks.
Yeah. Lokesh. Lokesh Kumar, can't hear you.
Hello.
Yes, I can hear you now.
Will we be always be able to come up with a divergence metric?
That we define, no? Yeah, see, if your question is, will we always be able to evaluate the divergence metric? The answer is no. That's why you need a lot of trick. All this GAN, etc., are actually kinds of tricks to evaluate this divergence metric. Will we be able to define a divergence metric? Of course, I will just, right now, I will define a few minutes.
I meant the evaluation.
Evaluation, no,
the,
not necessarily.
yeah.
No, we can't, no, because there is one apparent problem with this. The apparent problem is that this divergence metric seems to ask for px. We don't have px. That's our whole problem. Right? Now, how do we evaluate these divergence metrics when you don't have px? Is the question that we are going to answer in this course. And there are different tricks to do that. People generally compute a bound on this. You can't find this exactly. So you compute an approximation to this, which is computing a bound. That is what this evidence lower bound and all this expectation maximization, VAE, etc. do. We will see all that in detail. You can always define it, but can you compute it always? Perhaps not, depending upon what divergence metric are you looking at. That's the, I mean, see, in the rest of this course, we will only do this. We will pick a p theta, we will pick a d, and we will see how to solve that optimization problem. That's all. That's all we'll do in this course next. Okay. Okay. Yeah. Raghavendra.
Yes, sir. The first question is the choice of the original distribution, right, is also a model parameter. So, for instance, in this case, choice of the distribution, the original distribution that you try to fit. So here you try to fit the normal distribution.
No. Please. See, one again, kind request is please don't try to use the terms that I have not defined. I have never told what do you mean by fitting. Right? So I have defined learning, training, models, etc. Please try to use my terms anyway. So that apart, see, we are not making an assumption on px. Right? We are only saying that my px. We are making an assumption on parametric form. We're just saying there exists a p theta, a family of p theta, okay, of which my px is a member. You get it? When I make an assumption, let's say that p theta is a normal distribution, I'm saying that my px is also a normal distribution with certain mean and variance. That is the assumption that we are making. Understand? Now,
that is something that we need to choose upfront, right?
Let me complete.
There is a lot of noise.
Yeah, somebody unmuted. Okay, so let me complete. I'm saying, suppose you may assume p theta to be a neural network. What I'm trying to say is that there exists a set of weights for this neural network, which corresponds to my underlying px. Okay.
Yeah.
Now, what is your question?
No, but again, here we have chosen normal, right? And then the parameters are only mu and sigma, right? But I could have chosen a different distribution also.
I told you, right? I mean, that is your model choice. You choose anything that you want.
But yeah, in general, do we say that, the normal fits, or the normal is the better candidate?
We can't
most
say
cases?
at all. Definitely not. Because, if you take MNIST and if you want to model it by normal distribution, you are doomed. There is absolutely no way that there exists a mu and sigma that would make, that will give you the distribution of MNIST data.
So that is something that we need to decide based on the data.
Today people are you have to have a family p theta that is expressive enough.
Okay.
That would express a large class of density functions. No, normal density does not express a large class of density functions at all.
Okay.
isn't it? Because it can't even express a binom, I mean, like bimodal distribution. It can only express unimodal distributions, and most data will be by multimodal distributions, right?
Okay, and in case of neural network, can you just go little down? So basically, at the end, you get a distribution, but what you're shown here as the input is the z, the normal standard.
Yeah.
So
See, this
what
is
does it
one
mean?
choice. So you have a neural network that would take normal distribution as an input and gives you a distribution as output.
Okay.
I'm modeling it that way, no? I can choose, see, p theta is in our hand. We can choose our p theta to be anything. We can choose it to be anything. Now, if I choose it to be a neural network, then there are large sets of distributions that my neural network can express.
Okay, so it's kind of showing that you are transforming the normal distribution to some complex distribution using neural network.
Via this neural network,
okay.
Yes.
Yeah, okay, understood.
See, even in discriminative models, you do the same thing. No, you have to estimate p of y given x. So you take a neural network. Right? That would take x as an input and gives you p of y given x. This is exactly what a ResNet, etc. does, no? Now you can either make this p of y given x 1 by 1 plus e power minus x, e power w transpose x or something, in which case it becomes a logistic regressor. That is your p theta, right? The choice that you make on the model is what you call a model. You can make any choice for it. You can make it, you can say that, okay, it's a logistic regressor. You can take any parametric form for that and estimate the parameters. That's all. Yeah.
Yeah, got it.
Okay. Rajat?
Sir, my question is, if we have some ways to identify the real PX using some tricks or methods that, and you told we'll discuss later in this course, then identifying what we will achieve by minimizing the divergence, because knowing the real PX is something that we all interested in, right?
No, we can't. I mean, the whole problem is there is no way to know real PX. That's the whole problem.
Then how we will diverge, how we will calculate divergence?
I've not told
if
you
we don't
that.
know
No,
the
I
real
said,
PX.
that is one problem. That is one question that I will answer in a while.
We'll directly sample from there. Try to sample.
Yes. Please don't jump. There is a method to do. There is something called law of unconscious statistician and law of large number that we will use, and we'll use construct some bounds. Those are the things that we will do in this course. I've told you that that is some question that I'll answer. Now, how do you evaluate the divergence metric if you don't know PX is a question that I will answer. I have not answered that. Okay. But I want you to understand the philosophy, right? I mean, like what is happening? You given data, assume some parametric form on underlying PX, compute the divergence metric, and then adjust your parameters of your p theta such that this divergence metric is minimized. That's all. I mean, is this point clear? I mean, this is what I wanted to drive home. If this is clear, then the next question is, of course, what divergence metric, what form, how do you compute the divergence metric, etc. is what we teach in this course. Okay.
Okay, sir.
Is it okay?
Thanks.
Yeah. Okay. Any other question on this? Okay. Now we'll take up the, so now the next question is, given a pair of density functions, how to measure the distance or divergence between them. Right? This is a question that we should answer now. Okay, because one of the, I mean, there are three questions, right? How do you choose the model is the first question. Then the second one is how do you compute the divergence metric. The third thing is like how do you optimize, right? I will take up the second question first. We'll take all questions one by one, but this is more important, right? I mean, this is the first step. So given a pair of density functions, how do you measure the distance or divergence between them is the question. See, there are I mean, like many ways to do this. So there are things called F divergences that we will be seeing. Okay, and there are things called Wasserstein's distance or optimal transport, and there are things called maximum mean discrepancy (MMD). Okay, we will look at all of these one by one. Okay, but yeah, so how do you estimate? So you understand, right? Suppose I've given you 2 points in Cartesian plane. How do I know how close and far off they are? Is that just compute the Euclidean distance, right? If this is x1 comma y1 and this is x2 comma y2, then you know how to compute the distance between them, right? X1 minus x2 squared, whatever the usual Euclidean distance. Now, if you are given two density functions, how do you define, how do you measure divergences or distance between them is the question. Okay. What we will do is, okay, I will start with one famous divergence metric. Okay, so here is a question that I want to ask you. Maybe I should not ask you that, but see, as I said in this course, we will be looking at models like VAEs and GANs and diffusion models and so on, right? Which one do you want to start with? Do you want to start with GANs and then go to VAEs, or VAEs and then go to GANs?
Sir, first VAEs, then GANs.
Typically, I used to do that. I used to start with VAEs and then goes to GANs. But this time, I'm just thinking I should do the other way around. I'll tell you the reason. The reason is these diffusion models, right? Diffusion models are special cases of VAEs. They're actually hierarchical VAEs with a fixed encoding process. So now, if I do VAEs and then do diffusion models, right? I mean, it will be fresh in your memory, and I don't have to repeat things that I have done for VAEs. So now what perhaps we will do is, GANs are a very different class of models, and they are sort of out of trend now. People are not looking at GANs because of the problems that it comes with. So let us start with adversarial learning, okay? And perhaps then we will go to VAEs. So having said that, I will simply give you, an example of how to look at the divergence metric, right, and how to compute that, etc. And then from next class, we will go to adversarial learning, okay? So now let's take up this question. Given a pair of density functions, how to measure distance between them is the question, okay? Now to do that, let us look at this. Suppose, okay, there is an event A, okay, that is in the set of events F, okay, and I'm interested in a measure, okay, that quantifies the amount of information associated with it. Okay, do you understand? So what are we trying to do now? We are actually trying to derive a famous divergence metric between two distributions, which is called the Kullback-Leibler divergence or KL divergence. Okay, and to do that, we need some concepts of like basics of information theory. Okay, I'm just trying to derive that so that you understand where this actually came from. Okay, now suppose there's an event that is there in the event space, and what you are interested in is you are interested in a measure that would quantify the amount of information associated with it. Okay, now that measure, let's call that as some I of A, what properties do you seek in such a measure? I would say that the should be high for less probable events. Okay, should be low for high probable events. Do you agree? See, if I have to quantify the amount of information associated with a particular event, that measure has to be very high for less probable events, right? I mean, what I'm trying to say is, if I tell you that the sun rises in the west tomorrow, then it has a lot of information in it, isn't it? But if I tell you that the sun rises in east tomorrow, then it does not have any information. Do you see what I mean? So now this information measure that I associate with a particular metric has to be such that it should be high for less probable events and low for high probable events. Now, if you take the asymptotic cases of it, right? So the information that is associated with the entire sample space should be 1. Or let's say, okay, it can be that also. No, yeah, it can be infinity, right? It should be very high because the probability of sample space is 1, right? The probability of sample space is 1 because something, I mean, when you conduct the random experiment, some outcome will come. That is what this is saying. So the information that is associated with the sample space has to be infinity, and the information that is associated with the null should be 0, because I mean, if I or sorry, the other way around. No, sorry, I think I've switched it. Sorry. Yeah. The information associated with the sample space has to be 0. The information associated with the null should be infinity. Correct? That's the asymptotic case of what I've just mentioned. If I say that something from the sample space always happens, of course, I'm not telling you anything. If I say that something from the null space happens, then the null set happens, and I'm giving you infinite information. The other property has to be that the amount of information, right, that is associated the with the intersection that two events happen should be equal to the individual excuse me for this. The information associated with two events, in union of two events happening, have to be equal to the individual sum of individual informations if they are mutually independent. This makes sense, right? I mean, they have to add up. Basically, I'm saying that if there are two events happening together and if they are mutually exclusive, then the total information that is conveyed by both of them have to be the sum of information conveyed by individuals of them. Does it make sense?
So should it be I of A intersection be equal to null set, or just A intersection be equal to null set?
Yeah. Yes. Thanks. This is what it is. Yeah, thanks for that. The typo. Okay. This is okay, right? Now, in fact, I mean, these measures were proposed by Shannon. Okay, it's a great information theorist who is responsible for all the communication that we have today. That he defined this thing, right, to be the surprisal of a particular event as the negative of logarithm of the probability, okay, associated with that particular event A. I should not be writing this as script P because we have taken the script P for uh, the distribution functions, right? It's the probability of this event A. See, can you just take a minute and convince yourself that it will satisfy all three properties that we saw? Can you just take a minute and verify this? Is it clear to all of you? Okay. Okay, so this is for one event, right? So now suppose need to quantify the information in a distribution, right? What do we do? This is for one event, right? If we want to do it for the entire distribution, how do we do that?
Integrate all the values.
Yeah, just take an average, right, over all events. So let's say that this is the discrete display. I'll do it in a discrete distribution in a discrete, let's say that it's a discrete distribution for the ease of understanding. Discrete distribution, right? So now PMF are probabilities, right? So I'll say that I'll have to look at the negative of log of the PMF function associated with particular value xi. Okay, I look at this and I take an average of this with all possible values that this xi can take, which is px of xi, and just simply take the sum of all the values that it can take. So this will quantify the average information associated with the distribution px. Do you agree? This should give you, so because a negative log of pxi will give you the information associated with one event, okay, or one outcome. If you take the average of it over all the possible outcomes, then you will get the average information that is associated with the entire distribution. Okay, yeah, some people have questions here. Let me take question. Yeah, go on with questions.
Sir, I didn't get why the information associated with null set is infinity, and also why information associated with event A is minus log of probability A.
Sorry, I'm muted. Just give me a second. I'll answer that.
We can hear you, sir.
Hello, can you hear me?
Yes, sir, we can hear you.
Give me a minute. Give me a minute. Hello, can you hear me now?
Yes, sir, we can hear you.
Okay. See, the thing is, this is our definition. See, what I want is I want a measure that would take very high value for less probable events and will take very low values for high probable events. Okay. That is the measure that I want. Now, the asymptotic case, which is the extreme case, is the following: that if you take the entire sample space, then that is the most probable event, isn't it?
Yes, that will be.
That should have zero information. Okay. Similarly, the least probable event, which is the null, should have infinite information.
Sir, I understand the probability part, but how come that gets reversed when we associate with the information?
That is how we want, right? See, now, what are we desiring? See, okay. So I'll tell you some historical thing, right? The question that was asked is, if you say that an event has happened, you tell me how much information is conveyed in that, is the question. Now, intuitively, don't you think that an event that has very high probability, or which is very highly probable, conveys very less information? Historically, what happened is, the question Shannon was asking is, if I have to compress suppose I want to, I want to pass a message from point A to point B, and I want to.
Understood now.
Got it? No, it's
Yes,
easy
now I
actually.
understood.
Okay. Yeah. So, we defined the information this way: information content associated with an event this way, that it is the negative of log of probability associated with A. That's all. Okay. Okay. Astic.
Yeah, so I got it that we found out that this information about information of A is minus log of probability of A. But how does this union property satisfy with this?
And just look at it, no? The probabilities get multiplied if the events are independent, and there is a log, right? So log will get summed. Probability of A and B, log of AB is log A plus log B, isn't it?
Okay, if they're distinct. Okay, yeah, understood. Yeah.
That's why I give you a minute to just plug that
Yeah,
there
yeah, I
and
forgot
realize
that they
that.
are disjoint also. So yeah, okay. Yeah.
Okay, Sachin.
Yeah, thank you.
Sir, in this average function, will it be like capital P, right? This small p was for probability density.
I am saying it's a discrete distribution, right? So this is PMF, probability mass function, which is a probability by itself.
Sorry, can you tell me?
See, I said that it is a discrete distribution. Therefore, this P is a PMF function, probability mass function, which is it is actually a valid probability.
Okay.
Write it down. Okay, Sanket.
Yeah, so this union property that is there, basically A union B is IA plus IB. But if we consider a union of A with null set, means this the intersection will also be null. But then this property will not hold, no? Because A union null will be A itself. But then if we add them up, it will be infinity.
No, A union null is A. Okay, you can still represent that as I of A plus I of null, right?
But I of null is infinity, no? So
Yeah,
I
that
of
is
a
why
plus I of null will be infinity.
you're saying, I mean, maybe I should just add that for, so yeah, that will solve it. That's an edge case,
Okay.
right? Yeah. Yeah, Aditya?
So similar, just an add-on to that question. If B was, for example, an A complement over here, so I of A plus I of A complement, that would equal to I of omega, the whole
Correct.
subspace. So that should be 0, right?
Yeah, of course.
Okay.
Of course, by definition. Okay, so now there's a name for this. Do you know what this is called? Sorry, this is called. Sorry, this is called the
Entropy?
entropy. Yeah, this is called the entropy
Entropy.
of the system. This is the entropy associated with the distribution. That is, it's simply the average information that is associated with the distribution is called the entropy of the distribution. Makes sense, no? Makes a lot of sense. So basically, you define the information content for an event and just take an average over all possible events that are there, and that will give you the entropy, which is the average information that is conveyed by a distribution. That's fine. Okay, so now I actually have to now define the cross entropy and so on. It's 12:20 already. We started 15 minutes late. Do you mind if I continue for 10 more minutes or should I stop? Shall we take it the next class? See, if there is even one person who wants me to stop now, I will stop because I should not be continuing. Is there anybody who wants me to stop now? Let me know if you have to go somewhere and you have a hard stop. I'll stop it here. So let me take 10 more minutes. Now, suppose two density functions. P and Q. Now, if I compute so it looks like my screen has frozen. What do you think this will give you? Can somebody tell me what does this give me? Can I interpret this as can I interpret it this way? Can I say that it's the average information in Q about P? Can all of you see this?
Yes.
Right? This also has a name. Do you know?
Cross entropy?
This is the cross entropy. Between P and Q. Okay. Now, if I take this and subtract by this, how do I interpret this? Can I say that this is the information? Say that this is the extra information in P that is not in Q. Can I call it this way?
Sir, the first term tells us about, like, gives us the information about Q, right?
Information about P.
Like,
the first, here cross entropy is it? Cross entropy tells you that how much information does Q has about P.
no, about means
About
like
P.
Okay.
Right? And H of P tells you the information in P. If I take the difference between them, it will tell me how much extra information is there with P that the Q does not have.
And it should be subtracted by HQ, right?
I think
Sorry.
the terms should be reversed, right?
You mean HP minus HQ, is it?
Yeah.
HP minus HPQ. Otherwise, like this this is giving a sense that the term will be negative. Won't it, sir?
Hold on. Let me just see. See, there is a minus log there, no? Minus log also, it should be write this down. How does this look like? This is this is correct because there is a negative there, no? So in the definition of entropy, there is a minus. So when you subtract it, the minus will just go away and it will become plus. Understand? So basically, the difference between these two will tell you the extra information in P that is not in Q. Is that okay? Now this is equal to I this is correct, no? So there's a minus here. There's a minus of minus will become plus. So it will be P of Px log Px. And this term has a negative here. So log A minus log B is log of A by B. Is this okay? Do you know the name for this? This has a name. This is the
tail div.
Yeah. So this is one divergence metric that we will study in this course, that the KL divergence between these two distributions, Px and Qx, simply given by Px log. In fact, this is the last function that is used in most of the supervised discriminative machine learning to minimize the KL divergence between Px and P theta. Okay, see, the reason I did all this is to make you appreciate why this is a good metric. So I'll leave it for tutorials, okay, to show that KL is 0 if and only if Px matches Qx. Only if the underlying distributions matches, then the divergence will become 0. Obviously, right? Because the amount of information that is there in Q about P should not be more than what P has itself. So only if P and Q are exactly the same distributions, then the cross entropy matches with the entropy. And that is when the KL divergence becomes 0. So now this becomes a metric to measure how far a given distributions are. So now we will trace back to what we did. So we wanted to define or compute a divergence metric between the true density and the assumed parametric density, to quantify how far or close. KL is one way to do it. Does it make sense? So in the next class, what we will do is that given a particular model, how do you compute the KL and how do you optimize for it, etc., is something that we will see in the next class. Okay. So when you come to the next class, please come prepared. Just read whatever we have done in the previous classes, and also read about entropy, cross entropy, KL, etc., so that you have idea about what we are talking. Okay. Okay then, we are done for today. See you in the next class. And again, reminding, right, if you want to express something, have some opinion, the feedback form is there. It is completely anonymous. You can just go and put in whatever your comments are if you want. You go to my webpage. There is this ADRL course webpage, and there is that feedback form, and you can just simply put in your comments if you have any. Okay, that's all for today. See you next week. Have a nice week and bye-bye.
Thank you, sir.
Yeah, thank you, sir.
Just a second.
Thank you so
See,
much, sir.
next week, just a minute. See, next Saturday is this Ganesha Chaturthi. That's okay, right? We can still have a class.
Yes, sir, that's fine. We can.
Okay. Okay. Anyway, we are recording. If people want to take off, they can take off and see that later. Yeah, I'll have to ask my mother if that is possible, but yeah, I'll convince her. Okay. See, bye.
Yes. Thank you, sir.
Thank you.
Thank you, sir.